Hello, hello, hello. Good morning, folks. Welcome back to our first unit of second semester. We're going to be starting in on sound. We watched a Magic School Bus episode yesterday. If you haven't watched that yet and done the worksheet, you should probably do that before you watch this, because this is just going to add extra information that you don't need for the video, or for the worksheet. So keep that in mind. So today we're going to talk about waves. Okay, this is the first of three topics in our sound unit. First one's waves. Second one is sound waves, some attributes that are specific to sound waves. And then we're going to start doing some sound calculations, the math that I've been telling you is coming for quite a while. So we'll finally get into that. This unit suffers from much the same problem that the matter unit suffered from. The whole thing's vocab. Every single thing in this unit is vocab. So you have to know what the words mean to do the application end of things. So the vocab is very much embedded in the notes. At this point, I don't think I'm going to be putting out a worksheet or a doc that has just all the vocab terms. What I have done is I have put the definitions, I've made the text for those blue in the notes. So if you pull up the notes, you'll see the definitions are blue. So for example, our very first thing here, what is a wave? We're talking about waves. What is a wave? Well, the technical definition of a wave is a repeating periodic disturbance that moves from one place to another via medium. Via, in this case, means through. So wave has to travel through something. Okay, it can't travel through nothing. In fact, one of the things that, well, we'll save that. That's a discussion for sound. Which begs the question, what's a medium? That's kind of important. We don't mean medium as in someone who can talk with the dead here. Medium here is referring to some form of material. A lot of times when we're talking about a material, whatever it is something is made of or passing through, we'll call it a medium. It's just another term for something made of matter. Okay, it's another way of describing something that is just made of matter. For example, in an earthquake, the medium that the wave, because an earthquake is just a wave moving through the ground, which is the medium. It's a wave that's caused by the tectonic plates shifting, either, well, a couple of different ways that we're not going to get into, and that causes a vibration in the ground. So the ground is the medium that is propagating that wave. Now, propagation is just the process of a wave spreading from its source. So Ralphie pointed this out in the Magic School Bus episode. If you drop a rock in a pond, the waves, the ripples that move out from that, that's propagation. Okay, it's just the tendency, it's basically inertia, but for waves. Once you get a wave moving, it tends to keep going until something forces it to stop, like the bank of a pond, or in the case of the earthquake wave, it'll travel until it slowly kind of dies out. Each subsequent peak is a little less extreme than the previous one. That's why as you get farther and farther from the source, as that energy gets more spread out, the earthquake becomes less violent. The same thing tends to happen with waves. Unless you're putting any energy into them to keep them the same amplitude, they tend to peter out and die. But they will propagate as long as they have the energy to do so. Waves fall into two different categories or classifications: longitudinal waves and transverse waves. Longitudinal waves are hard to visualize, and we're not going to do too much with them, other than saying that the difference between these is the oscillation of the wave. Okay, so in a transverse wave, I'm going to start with number 2 here because it's the easiest to picture. The wave is oscillating perpendicular to the direction it's traveling. This is the ripples on a pond. So if this is the surface of the pond, you drop the rock in here, the wave is going to propagate or travel this way, but the wave oscillates up and down. That's a transverse wave. So the ripples are rising and falling vertically while the wave is traveling horizontally. That's a transverse wave. In a longitudinal wave, the oscillation is in the direction of the propagation, which is a lot harder to visualize. That's why I have the slinky example thing that we're going to look at later for the video. I don't know how I'm going to do that yet because it takes two people to hold the slinky and someone else will have to be recording. So that video might not be up today. That might take me a minute to get logistically, but I will try to get that posted as well. So based on this discussion, what kind of wave is this? What is this a diagram of? Is it a transverse wave or a longitudinal wave? I hope you said transverse because this is a transverse wave. Okay, this is a diagram, a pretty standard diagram for a transverse wave because transverse waves are how most of the waves that we can actually see propagate. We can see transverse waves very, very easily. Most of the things that propagate as longitudinal waves, you can't really see them. It's a lot more complicated, which is, again, why we're not going to mess too much with that in this video. I am not going to have you label or identify stuff in a longitudinal wave diagram. You can draw a diagram for this, but it's weird looking, and I'm probably not going to do that unless you guys really, really want me to show you one. But you are going to have to label, identify, and come up with information about a diagram for a transverse wave. So that's what we're going to be focusing on here. Now, waves have... Oh, man, I need a little more space. Let's do that. Okay. So waves have 5 aspects, 5 properties that you can pick out looking at a diagram. They are these first 5. Okay, the first is the equilibrium position. Now, what does equilibrium mean? Equilibrium is where everything is stable. Everything is mellow. It's constant. It's where stuff prefers to be, is in equilibrium. In the context of a wave, equilibrium is the flat surface of the pond. That's the pond at equilibrium. When you drop the rock in, the wave starts to disturb the equilibrium of the pond. So the equilibrium position on a wave is the position that the material is trying to get back to. So this here, this line, that's the equilibrium position. It's always going to be the center of the wave. This is, again, something you can't really pick out very easily in a longitudinal wave. So this is the position the medium, or the matter, that the wave is propagating through, is trying to get back to. Okay, it's where it wants to be. Before the wave showed up, this is how the medium was oriented. Okay, some kind of flat surface. Okay, once the wave comes through, it looks something more like this. And it's no longer at equilibrium. Crest or peak we use interchangeably. I trust this is pretty obvious. This is just the top of the wave. So there's a crest here, there's a crest here, there's a crest here, and there's a crest here. Trough is the opposite of a crest. It's the bottom of the wave. So here's a trough, here's a trough, here's a trough, and then here's a trough. Amplitude and wavelength are distances. Okay, I'm going to pause this to make sure I know how to use this new whiteboard program, and then I'll be back. Okay, I think I have adequately refreshed myself on this. So, amplitude is the maximum displacement from the equilibrium position. Okay, now displacement is a kinematics term that we haven't talked too much about yet, but if you think about it, you should be able to figure it out. Displacement is how far you are from where you started. Okay, so if I start standing here and I move here, my displacement is however far I have gone. Okay, maybe 3/4 of a meter. Okay, that's displacement. It is a numerical measured distance, and this is one of the calculations that you'll be doing stuff with later. Okay, there are two places where you can find displacement. You can find it between a trough and the equilibrium position, or you can find it between a peak and the equilibrium position. Now, to clarify, this is only the exact point that is the farthest away, maximum displacement. It has to be the biggest distance on the wave. Okay, now for this, we are generally going to assume that the peaks are the same height and the troughs are the same depth, that they are not significantly changing as time goes by, which is, in a short span, is not an inaccurate assumption. They tend to propagate and decay very, very slowly. In terms of sound, the volume is the amplitude. Okay, as you turn the volume up on your, good Lord, I was going to say on your speaker or on your stereo, but on your radio, let's go with that. As you turn the volume up, you're increasing this distance, the amplitude of the wave. In the Magic School Bus video, it talked about a big vibration versus a small vibration. That's the amplitude. The bigger the vibration, okay, the higher the amplitude, the more displacement we see. In a smaller vibration, we'll have a smaller displacement or a smaller amplitude. So this distance will be small in a quiet sound or in a small wave, and in a large wave, this displacement is going to be larger. The other part of this, the last part, is the wavelength. Now, the wavelength is the distance from one wave, where one wave ends and the next wave begins. So technically, a wave starts at the equilibrium position, goes through a crest, back through the equilibrium position to a trough, and then returns to the equilibrium position. So, this is your wavelength, which, by the way, wavelength is abbreviated with the letter lambda. This is a Greek character. It's kind of an upside-down Y. It's a little bit of a script, but if you want to write it like that, that is perfectly fine. But I'm going to be using this for wavelength most of the time. So this is the definition of your wavelength. It's the distance when it is the distance for one full wave. So a peak, a trough, and a return to the equilibrium position. This is not practical to measure most times, though, because you have the equilibrium position here and 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 here, and it's crossing the equilibrium position 3 times in one wavelength. That makes it much more likely that you make a mistake if you try to measure the wavelength here. It's not a good option. But there's a pretty obvious surrogate to this. If this is the equilibrium position, if this is the distance of a wavelength, what is this really? Well, it's the distance that it takes for one full wave to go by. Here we are rising from the equilibrium position. Here we are rising from the equilibrium position. As long as we are starting and ending at the same point on a wave, the start and the end, it doesn't really matter where we define the start and the end. So it's actually much easier to define wavelength as being the distance from one peak to the next peak, or from one trough to the next trough. All 3 of these would be valid ways to measure the wavelength. However, this would not be a valid measure of wavelength. going from here to here. That is not a wavelength, okay? Because you're going from a rise through a fall, through another rise, this is where it should end, and to another fall. This is more like 1.5 wavelengths. And this is the number one mistake that I see people make on stuff like this. Okay, so that is not a wavelength, and that's something you're going to have to kind of be mindful of as you're moving through this. Now, the last two properties of a wave are not visual properties. These are mathematical concepts more than anything else. Okay, and this is frequency and period. These two are very, very closely related. Frequency is how many times a wave oscillates. No, sorry. Yeah, I said, okay, I was saying that right. It's how many times a wave oscillates in 1 second. Okay, so this right here is a very small segment of a wave. This might represent 2 seconds. This might represent a millionth of a second. How many crests are going by in 1 second? That's the frequency. The higher the frequency is, the faster the wave is moving. It's a way of measuring the speed of the wave. Now, it's not perfect because that also depends on what the wavelength is, which is where our calculations will come into play later on in the unit. Because just because your frequency is 1 a minute, well, if your wavelength is a mile, then yeah, you've only got 1 wave going by every minute, but that's still moving pretty fast if you're covering a mile in a minute. That's 60 miles an hour. That's moving pretty significantly quick. Now, it'd be short, it'd be pretty slow in terms of wave propagation, but that wavelength is really, really important too. And like I said, when we get to topic 3, we start doing calculations. We'll look at how these two work together to get that velocity. How fast is the wave actually going? But this is a way we look at how fast is the wave oscillating. How fast is it moving up and down? Okay? And then contrasted with that is the period, which is basically just the frequency, but upside down. This is how much time it takes for 1 oscillation to be completed. How long does it take for 1 full wave to go by? Does this take a minute? Does this take an hour? Does this take a second? Does it take a millionth of a second? Do you get a million waves going by in 1 second? Okay, that's the period. When we talk about period, we're talking about time. Frequency is how often. Period is how long. And that might be worth jotting down. How often, how long. Now, you are going to have to identify these 5 things on a wave diagram. And that is what one of the worksheets is meant to practice. Flip side of that, you may be asked to do some calculations with some of those, but that will be something that we'll do very, very minor bit with until we've actually had time to practice. You cannot visually identify these. These are math. These you aren't really going to see until we do much with other than definitions, until we get to topic 3. Once we get to topic 3, wavelength, period, frequency, and velocity will all be something we're doing a lot with. I don't remember exactly how many practice calculations there are, but I think there's 40 or 50 of them. So we shall see if you get what's going on there. The last thing on this we need to talk about. Oh, I need to clear that. You know what? I'm not going to get into proportionalities on this because I know I talk about it when we start doing the calculations. So I'm just going to say period and frequency are inversely proportional. That means that if the frequency is going up, the period by definition must go down. Okay? If the period is going up, the frequency must be going down. And I may need to come back and talk more about this because energy, I don't remember if energy is in this part or in the next part. So this may be something I have to cover later. We'll see. But that is going to wrap this up. I do have another video coming for sure that shows the Slinky example. Hopefully I'll have that done before too long. And then obviously I may have to do a follow-up video that goes through proportionalities because I don't remember if they're in this part of the unit or not. But this video just hit 20 minutes, so I want to go ahead and wrap up. So have a wonderful whatever time of day it is, and I will see y'all next time.